And we're recording. All right, let's do it. Good afternoon, everybody.
Good afternoon.
How's it going? All right. What's today? Wednesday?
I think.
You're not doing a good job of hiding it, man. It's all good. Remember, what's the cell phone policy? Pretend to hide it from me. Yeah. Otherwise, you can have it out. Okay. Are there any other questions, comments, concerns before we start today? Don't forget that the stuff for Unit 1 is due on Friday. Yes?
So like on the self-study guides, like some of them, like there's not enough like space to write. Is it okay if we like do some on paper?
You're supposed to do it all on paper.
Oh, so like, cause like I printed it out and then like.
Don't do that. I hate people who do that.
Yeah, all right. I guess I'll have to rewrite.
Yeah. Yeah. I think it says in the instructions on a separate sheet of paper. Yeah. It's okay though. You don't have to rewrite it if you don't want to.
I'll rewrite it.
I'll allow it this time.
It's pretty tiny.
Okay. Yeah. Cool. Any other questions? Yeah.
So from yesterday, the very last thing we talked about when you said, checking them by going like individually, do we go from left to right or right to left? It's like, because I just got confused with the F equals A, B to the, or 1 plus C. I was unsure about
Say that one more time.
So for the gates, we were
Hold on.
talking about yesterday,
Back
very,
here.
yeah, there.
Yeah.
So when we check them, we go from left to right or right to left? For
When you check what?
So when you start putting like inputs when it's like 0, 0, 0, and so you go through the line.
Okay, so it's not left to right, but it's like in order of the things that you
Just
need,
the
right?
operation.
So for example, so you're given A, B, and C, right? That's what
Yeah.
you start with. Those are the inputs. But to get A and B naught, we gotta have B naught first, right?
Yeah.
So it sort of follows kind of an intuitive track, right?
Yeah.
I mean, you gotta do B naught first in order to do A and B naught. You gotta do A and B naught in order to do A and B naught or C,
Okay.
right? So it's not really, it's about left to right, it's about,
The process of like going
Yeah.
through things.
Mm-hmm. Yeah, so you can't do a column for a thing that you haven't figured out yet.
Okay.
Cool. Any other questions? All right. In that case, let's do this. So we're going to start off today talking about the fundamental operations of Boolean algebra, right? We got some basic rules, we got some basic operators. We learned how to make expressions. Now we want to be able to do things with them. So that's what we're talking about today. Fundamental operations of Boolean algebra. Okay. So they kind of group into sort of natural groups, and the first ones we're going to look at are called operations involving 0 and 1. All right. So here we go. What is x or 1 going to be equal to? Just 1, right? Because if x is 0, 0 or 1 is 1. If x is 1, 1 over 1 is 1. So if anything ORed with 1 is just equal to 1. What about x or 0? Equal to x, yeah, good. By that same token, what about x and 1? It's going to be equal to x, yeah. Right? Because if 0 and 1 is 0, and 1 and 1 is 0, so it's going to be equal to x in either case. What about x and 0? It's going to be equal to 0. All right. Questions about those guys? All right, let's keep it moving along. The next ones are called the idempotent laws. Idempotent meaning just an operation with itself. X or x is equal to what? It's equal to x. And x and x is equal to what? Somebody's got to say it there. equal to x. Right? So XOR anything ORed itself is itself, and anything ANDed with itself is itself again. Next up, we have the involution law. Which basically just says that if I take x naught and not it, what do I get? I get x. So, another question? All right, we're just flying through these. They're really simple, and the only thing to do is just commit them to memory. Next one is called complementarity. And that is XOR x naught is equal to what? What was it? 1, good. Right, because it's going to be 0 or 1, or 1 or 0. What about x and x naught? 0, good. All right, the next few are kind of silly and boring. They're the ones from regular algebra. The associative property. It's the one that says the order in which you do equivalent operations doesn't matter. So if I do x or y and then or z, it's the same thing as doing x or y or z. And then for and x and y, and z is the same thing as doing x and y and z. And then the commutative property. Is the one that says the order doesn't matter, so x or y is the same thing as y or x. And same deal, x and y is equal to y and x, so you can rotate them around. Then we come to the distributive property. This one is slightly more interesting because it has a thing that isn't in regular algebra. There are actually two distributive properties in Boolean algebra. One is the one you're probably most familiar with. That's the one that says x and y or z is equal to x and y or x and z. Right? You distribute the x into the y or z. But it also has a second distributive property, which is really handy, and it looks like this: x or y and z is equal to x or y and x or z. Sort of the flip side of that same property. Ugh. I promise we'll do more than just list properties and laws today. Do you have a question about that, man?
Can you explain the second one again?
Well, I mean, there's nothing to explain yet other than that is the property, right? X or y and z is equal to x or y and x or z, right? Because in Boolean algebra, the ors and ands are kind of reversible, right? This is kind of the same thing, where you have x distributing into y or z. This is kind of what you're used to looking at from regular algebra. The same thing is happening here. You're having an or that's distributing into the and operation, y and z. It doesn't look like it looks in regular algebra, so it seems kind of strange at first, but it's the same concept. But for now, just memorize it. Okay. And the last of these properties is called De Morgan's law. It's the only one that gets to be named after a person. And it says that if we take quantities, x and y, and invert them, so x and y, all of that inverted, is equal to x naught or y naught, And the same deal, x or y prime is equal to x naught and y naught. This one stumps a lot of people in the beginning, right? Because you intuitively want to think that x and y naught is equal to, like, this is what it's equal to, right? That the inversion happens sort of on the inside. It distributes, but it doesn't, right? It flips over the sign as well. It's kind of what I meant about and or being swappable. When you invert an and operation, you get an or, right? If you invert an or operation, you get an and. That'll come back in a big way on Friday. So those are the basic fundamental theorems and properties of Boolean algebra. There's not much interesting there, but you just got to know them, you got to have them committed to memory so that we can use them. Cool? Any questions about those?
These are in our book, correct?
Yep, everything's in the book. Okay, so I kind of like, we have some more stuff to list, but these are slightly more interesting. The goal of this is to simplify things. So there are a bunch of repetitive operations that happen a lot when simplifying Boolean expressions. They happen so much that some folks did you a favor and just grouped them up and called them theorems so that you could do them all in one shot. These are called the simplification theorems. What was that? Do you have a question or a comment?
Yeah, it was in the tape.
Okay. Theorems. The first one is called the uniting theorem. And it says that x and y or x and y naught. You want to tell me what that's going to be equal to? At yx. Other than just sort of it feels right.
The y's cancel out.
You're on the right track, right? Yeah, so it's not that the y's cancel out, it's the y's are redundant, right? So it's x and y, or x and not y, right? In both cases, it's x, but they're being ended with y and it's inverse, so y is, not that the y is canceled out, it's just that y is irrelevant. So x and y, or x and y naught, simplifies to x. On the flip side, it has x or y and x or y naught is also equal to x. That's the uniting theorem. Next up, the absorption theorem. Which says that x or x and y, now what's that going to be equal to? It's equal to x. How come? It's good, yeah. Get out of the habit of saying plus. It's or, right? Gets people in trouble. Yeah, but she's absolutely right. So if we were to use the distributive property to factor out, we would have x and 1 or y, right? And we know that 1 or y is equal to what? Right? Anything or 1 is equal to 1. So that's x and 1. And anything anded with 1 is equal to itself. So it's just equal to x. So the absorption theorem, x or x and y is equal to x. On the other side, we've got that x and x or y is also just equal to x. The absorption theorem. Not quite as powerful as the uniting theorem, but still pretty handy. All right. I'm gonna give myself some. I'm gonna leave that. Okay. 3. It's called the elimination theorem. Looks a lot like uniting, but has one subtle difference. Actually, it looks a lot like absorption, but has one subtle difference. It's x or x naught and y. And that one I'm just going to write out for is equal to x or y. So everyone see the difference between elimination and absorption? Right? In elimination, that x that is ending with y is also inverted. Because it's inverted, you can't get rid of all of it, you can only get rid of the inversion. And also x and x naught or y is equal to x and y. Elimination. And the last one, the one that freaks everybody out, is called the consensus theorem. And this one's weird. This one says that x and y, or not x and z, or y and z is equal to x and y, or not x and z. We will have a whole class devoted to the consensus theorem in like a week. For now, just take my word for it and memorize it. All right, now we're done listing things. Any questions about the sort of structure of the simplification theorems or the laws? Like I said, there's not much to talk about other than know them so that we can use them. Put them on flashcards, commit them to memory. Yes, ma'am?
Why is the elimination theorem the second one? Why is it x?
Say that again.
Like on elimination theorem, the second one you looked at, why is it xy?
Why is it xy?
You have the answer?
Well, check it out. We could do it. We could work it out, couldn't we? So we could do. So if we have x,
Oh, wait,
well, we've already started now. Right? What theorem? What property do we use now? Distributive, right? So then we'll have x and x naught, or x and y. What is x and x naught? It's complementarity. It's 0, right? So we have 0 or x and y. What is 0 or anything? It's that thing, right? So yeah. So x and y. Cool. All right. Any other questions? Yeah.
Do you need to know the names on these?
You bet, man. Otherwise, where's the fun in it? They have these cool names like complementarity. I had to write them down. Yeah, a few of the questions, like long term, no, you don't need to know. But I think on the assignment, it asks you like, hey, like it'll show you like what the simplification was and say, hey, identify what theorem was used. In previous iterations of this class, I was really mean, and in every operation, every like simplification, I would make the students like write the name of which theorem or property was used on every line. My wife is an algebra teacher, so we take that sort of stuff seriously in our household. But I've walked back off of that. So, all right. Any other questions about these? We're all about theorems and properties, man. Okay, so let's do some interesting stuff. Let's do some simplifications. So let's say we have a function z is equal to a naught and b and c, or a naught. What does it simplify to you, and what theorem did you use to simplify it?
Could you use the distributive property?
What's that?
Could you use the distributive property?
You could, but you shouldn't.
You shouldn't?
No.
Elimination, the elimination theorem.
What's that?
Elimination theorem.
It's not the elimination theorem. Absorption? Why absorption?
Seems like if you take the A prime as common, anything or the one is the one. And then that and A prime would just be A prime.
Alright. You're totally right. Let's be a little more formal about it. Absorption. Alright, remember that's the one that says that x or x and y is equal to x, right? So we can substitute. What's x equal to in this case?
A prime.
A prime. And what's y equal to?
EC.
B and C. The important thing here, notice that you can use like larger expressions in your substitution. So yeah, so if a prime, x is a prime, and y is equal to bc, that means our answer, z is equal to what?
A prime.
Simplifies to a prime. Good. Any questions about that one? All right, well, folks are still jotting that down. Let's do the next one. All right, let's say that the function f is equal to brackets, I'm going to put a or b prime c or d or e and f then a or b prime c or d or e and f, that prime and capped off. Same game. Simplify it and tell me what expression you used, or what simplification theorem you used. Okay, how come? Use the uniting theorem, all right. Let's see, uniting says that what, x and y or x and y naught is equal to x. In this case, what is your x equal to?
A plus B prime C.
Not plus.
Or B.
Yeah, a or b prime c, that's that guy. Oh, except I wrote the wrong one, didn't I? I should have used the other uniting theorem. I made the same mistake in my first class too. It's this one, x or y and x or y naught is equal to x. In this case, what's y equal to?
D or E and F.
Good, d or e and f. So you can see that it's been inverted there and it's just left alone there. So after simplification, what's our f equal to?
Oh, just A plus B prime C.
Not plus.
Oh, or B prime C.
Good. All of that simplifies to just a or b prime c. Okay. So the trick is just got to look and see what stuff is repeating, what stuff is mimicking the patterns that you see in those theorems. Any other questions about that one? All right. Let's do one more example. Let's say that z is equal to A, B, or C, and B naught and D, or C naught, E naught, or A, B, or C prime. Elimination? I think so. So elimination says x or x naught and y is equal to x or y. So in this case, what's your x equal to? Not just A, B, or C. Prime, the inverted one, right? Just because this term is inverted doesn't mean that it can't be the one that can substitute for x, right? And it's the one that's by itself. The formula is x or x naught and y, right? And this, A, B, or C, is still the inverse of A, B, or C naught, right? So that means x in this case is equal to A, B, or C naught, right? And y is equal to what? Good. B prime D or C prime E prime. Which means our final answer, Z is equal to x or y, which means it's A and B or C prime, or B prime D or C prime E prime. Yes?
So could you explain again why did you take x as A and B or C and like prime and not just A or B and A and B or C?
Because A and B or C is not the term, so the structure is this, right? X or its inverse and y, right? Up here, the term that is by itself is A, B, or C inverse, not just A, B, or C by itself.
Oh, okay. So that,
Yeah, and then the whole thing gets inverted, right? This is x prime, once we do the substitution.
okay, good.
Cool. All right. So, are there any other questions about doing those simplifications before we move on to something else? Cool. All right. So, next up, oftentimes it's really helpful to get our expressions into a sort of form that we're used to working with. Makes the simplification process a lot easier. It makes designing our circuits a lot easier. And there are two what we call standard forms for Boolean expressions. So I'm going to say two standard forms of Boolean expressions. The first one is called sum of products form. Or SOP for short. And the second one is called product of sums. POS. All right, let's talk about the first one. Sum of products. So a sum of products is, here's a definition, a Boolean expression. Not a Boolean expression, a Boolean expression. Which contains, or in which, all product terms are terms of single variables. We'll explain what that means in just a second. Are terms of single variables. So an example of a sum of products expression would be this: A and B naught, or C and D prime and E, or A, C prime and E prime. All right? So when we say terms, we're referring to these and operations that are kind of hanging out by themselves and being or together. Those are the terms of the expression. So we say it's a sum because we use the or symbol, which looks like addition. So it's like a sum of the product, which is the and product terms. And when we say of a single variable, it just means that any variable of the function only appears once in the expression. So we couldn't have A and B prime, right? Any questions about the gist of this form? Cool. Sum of products can also have terms of single variables, or terms of one variable. And what I mean by this is something like this: we got A, B, C prime, or D, E, F, G, big old term, or H, right? We're allowed to have just that one term, that one variable just hanging out by itself, and that's valid. Likewise, we could have something like this. We could have A, or B, or C, or D, E, F, right? This is also a valid sum of products expression, even though most of the terms just have one single variable. Are we good on that? Okay. What about this? Let's see. A or B and C, D, or E and F. Is this one a valid sum of products expression? No. What's wrong with it?
Yeah, the product of the sum.
Yeah, this business hanging out on the inside, right? It's got to be that nice, clean, just ands separated by ors, right? So this isn't a valid sum of products. But the important thing is we can turn it into a valid sum of products. So let's write this: sum of product expressions are obtained by applying the first distributive property. The first distributive law. That's the one that says x and y or z is equal to xy, or xz. We also call this multiplying out. The expression. So whatever expression you have, if you want to get it to sum of products, you multiply it out by distributing. So let's use that as our example. A or B and C, D, or EF, what are we going to do? Any takers? Exactly, right? A and CD or B and CD. We're going to distribute the CD into the A or B. So we're going to get A, CD, or B, CD. And EF is still just fine, right? Now it's a valid sum of products expression. So we're just going to multiply out by using that distributed property until we get it looking like that, okay? Any questions about the sum of products formula? We're going to use it a ton. Yeah?
So it just can't be in parentheses? Is that what you're saying? Or the things where it was repeating?
It's not about the parentheses.
Okay.
It's about the fact that we had this expression being ended with an expression that contained an or, right? Parentheses are an accident, but it's about the fact that there was that or term.
Or, so it has to be one.
Yeah, it's going to be one sort of uniform, continuous looking thing. All right. So that's sum of products. Up next, product of sums. Basically the same definition, Boolean expression. But in which the sum terms are terms of only one variable. An example of that is going to be this: A or B naught and C or D naught, or E and A or C naught, or E naught. So it's like the opposite of the sum of products, right? Where before we had ands that were grouped together by ors, now we have terms that consist of or operations that are connected by ands. And all the same rules still apply. We can still have single variable terms. So for example, we could have A or B and C or D or E and F, right? That's still valid. Or we could have something like A and B naught and C, or D and E and F. Not as clean looking, but it's valid. Single variables connected only by and operations. We won't use product of sums as often as we will sum of products, because it's just not as pretty to look at. Now let's see, how about this? A or B and C or D, or E and F. And you can probably guess this is not a valid product of sums, but what's wrong? Yeah, we have this E and F term hanging out over here, right? In the same way that before we had that, or term in parentheses, here we have this, or term that's sort of hanging off to the side. That's messing up the flow. But just like before, we can convert it to product of sums using a pretty simple process. So POS can be attained by factoring, which is to say by applying second distributive. And that's the one that is x or y and z is equal to x or y and x or z. So just like before, let's use this as our example. A or B and C or D or E and F. In this case, what is our x equal to? E and F, good. And what's our y equal to?
A or B.
A or B, good. And our z?
C or D.
C or D. Fantastic. All right. Now that's going to get us A or B or EF and C or D or EF. Are we done? Nope. Is this product of sums? No, why not? What's that?
E and F is still there.
Yeah, because the sum terms have to be terms of just single variables, right? We have A or B or E and F, right? Still hanging out in the middle there. So we have to distribute or factor one more time. And not just one more time, we have to do it separately for each one. Oop. Almost out of time. Okay. So we're still going to use the second distributive to factor out, but we're going to do it each now for them separately, right? So for this first one, what's x equal to? A or B, good. And what's y?
C or D.
No.
Oh, wait.
Say again? E, good. And what's z? And z is f. Could I flip those? Could I say that y is f and z is e? Yeah, right, it wouldn't make a difference. Now what about for the second guy? What's x in this case?
C or D.
Good, C or D. And what's y? E, good. And what is z? F, fantastic. So when we put all of that together, we're going to get A or B or E and A or B or F and on the next side C or D or E and C or D or F. There we go. Now it is a valid product of sums expression.
Yeah.
All right. Any questions about getting your stuff into sum of products or product of sums?
I'm just curious, do these two functions do different things, or are they just different expressions of the same thing?
They are different expressions of the exact same logical operations. So you can take one expression, you can convert it to sum of products, and you can convert it to product of sums. The truth table in both cases will be exactly the same. Fundamentally, it will come down to what kind of logic gates you're going to use to build the thing. Right? So this one, product of sums, has a bunch of OR gates that all feed to an AND gate, and sum of products has a bunch of AND gates that all feed to an OR gate. Cool? All right, well that is all for today. If there are no more questions, comments, or concerns, thank you so much. Yeah, I'll see you guys on Friday. Be safe.